This is part 1 of lecture 2.1 of Math 108, Direct Proof. In this video, we will introduce the concept of mathematical proof and learn how to give a direct proof of a conditional sentence. Mathematical results are often presented in the form of theorems. A theorem is a true statement that describes a pattern or relationship among quantities or mathematical structures. A mathematical result may also be called a proposition, lemma, corollary, or claim, depending on the relationship of that result to other results within a body of mathematical work. A proof is the justification of the truth of a theorem. It usually involves a process of deduction from first principles using the rules of inference and valid argument forms. First principles include a set of undefined terms, which are concepts that are fundamental to the context of study, together with a set of axioms or postulates, which are an initial set of statements that are assumed to be true and which describe properties of and relationships among the undefined terms. For example, in Euclidean geometry, the concepts point, line, and plane are undefined terms. Their properties and relationships with each other are described by the axioms of Euclidean geometry that you learned in high school. In any mathematical theory, axioms are used to deduce theorems, which describe more complex properties of the undefined terms. These theorems, in turn, are used to deduce more theorems, and so on. A proof of a theorem uses the rules of inference and valid argument forms, the axioms, and other theorems which have been proved earlier, that is, other results whose proof does not rely on the theorem that is currently being proved. A valid proof of a theorem follows a prescribed outline that depends on the logical structure of the statement in the theorem, that is, on the underlying propositional form of the theorem. For a given propositional form, there may be more than one valid proof outline. We will organize our lectures by describing the underlying propositional form of the claim that is to be proved and give a valid proof outline corresponding to that propositional form. We begin with direct proofs of conditional statements. Note that the word direct does not mean easy. This refers only to the proof outline used. Let us assume that the statement to be proved has propositional form if P, then Q. A direct proof of this statement begins by assuming the condition P. Then we use a sequence of logically connected steps to deduce the condition Q. Here, by sequence of logically connected steps, we mean a sequence of statements P1 up to Pn, with P as the first statement and Q as the last, such that each Pi for I from 2 to n is a valid deduction from any of the previous statements, the axioms, or any of the theorems proved earlier. In the next examples that follow, we will work with real numbers and shall assume as true the axioms of real numbers. For brevity, we will use the following labels: E1 to E5 for the 5 properties of equality, F1 to F6 for the properties of addition and multiplication, and O1 to O4 for the properties of the order relation. In addition, we will use the definitions of subtraction, division, and less than. Assume throughout that the letters A, B, C, and D represent real numbers. For the first example, consider the claim, if A plus C equals B plus C, then A equals B. Let P be the statement A plus C equals B plus C, and let Q be the statement A equals B. This is a conditional sentence with antecedent P and consequent Q. A direct proof for this statement begins by assuming condition P, that is, that A plus C equals B plus C. Then Using a sequence of logically connected steps, we deduce condition Q, that is, that A equals B. As a convention, we will use a square symbol to signal the end of the proof. Alternatively, you may use the letters QED, which stands for the Latin phrase quod erat demonstrandum, which means that which was to be proved. We now show the proof. For now, we shall include the complete list of the axioms used in deducing the statement at each step. Later, we shall reduce the details to only the most essential. Do not focus too much on the mathematics or the level of detail. Rather, pay attention to the way that the argument is structured. Assume that A plus C equals B plus C. By the existence of additive inverse elements, which is axiom F6, there is a real number denoted by minus C, such that C plus minus C equals 0. Observe that we also applied existential instantiation in this step by calling this number minus C. Since minus C is a real number, it follows from the addition property of equality, which is axiom E4, that adding minus C to A plus C and to B plus C produces equal numbers. That is, the sum of A plus C and minus C is equal to the sum of B plus C and minus C. Applying the associative property of addition, we get that the sum of A plus C and minus C is equal to the sum of A and C plus minus C. And the sum of B plus C and minus C is equal to the sum of B and C plus minus C. Hence, by the transitive property of equality, we obtain that the sum of A and C plus minus C is equal to the sum of B and C plus minus C. Since C plus minus C is 0, the left side of the equality is equal to A plus 0, and the right side is equal to B plus 0. By the transitive property of equality applied twice, we get the statement A plus 0 equals B plus 0. By the existence of additive identity element, which is axiom F5, we have A plus 0 equals 0, and is equals A, and B plus 0 equals B. By the transitive property of equality applied twice, we get A equals B. This ends the proof. As a variation, consider the case where the claim is a conditional sentence whose antecedent is a conjunction. For this propositional form, we treat the conjunction as a single statement and begin the proof by assuming both conditions in the conjunction. Using a sequence of logically connected steps, we deduce the conclusion Q. For example, consider the claim if A times C equals B times C and C is not equal to 0, then A equals B. Let P1 be the statement AC equals BC and P2 be the statement C is not equal to 0. Let Q be the statement A equals B. Then the claim is a conditional sentence whose antecedent is the conjunction of P1 and P2 and whose consequent is Q. A direct proof of this statement begins by assuming that the conditions AC equals BC and C is not equal to 0 both hold. Using a sequence of logically connected steps, we end by concluding that A equals B. We now give the details of the proof. Assume that AC equals BC and C is non-zero. Since C is non-zero, it follows from the existence of multiplicative inverse elements that C has a multiplicative inverse, which is the real number 1 over C, such that C times 1 over C is 1. Since C Since 1 over c is a real number, it follows from the multiplication property of equality that AC times 1 over c equals BC times 1 over c. By the associative property of multiplication, AC times 1 over c is equal to A times the product c times 1 over c, and BC times 1 over c is equal to B times the product c times 1 over c. By the transitive property of equality applied twice, we get A times the product of c times the product c times 1 over c is equal to B times the product c times 1 over c. Since 1 over c is the multiplicative inverse of c, the product c times 1 over c is equal to 1. Hence, by the multiplication property of equality, the left side of the equality is equal to A times 1, and the right side is equal to B times 1. By the transitive property of equality applied twice, we get the statement A times 1 is equal to B times 1. Since 1 is the multiplicative identity element, we know that A times 1 equals A and B times 1 equals B. Applying the transitive property of equality twice, we get that A equals B. This ends the proof. Consider the case where the claim is a conditional sentence whose antecedent is a disjunction. Recall from a previous exercise that the propositional form, either P1 or P2 implies Q, is equivalent to both P1 implies Q and P2 implies Q. Hence, to show that either P1 or P2 implies Q, we need to prove the statements P1 implies Q and P2 implies Q. The assumption that P1 holds is called case 1, and the assumption that P2 holds is called case 2. Our proof, therefore, must have two parts. First, the proof that P1 implies Q, and second, the proof that P2 implies Q. For example, consider the claim, if either A equals 0 or B equals 0, then AB equals 0. Let P1 be the sentence A equals 0, P2 be the sentence B equals 0, and Q be the sentence AB equals 0. Then the claim is a conditional sentence whose antecedent is the disjunction of P1 and P2, and whose consequent is Q. To prove the claim, we need to show that if A equals 0, then AB equals 0, and if B equals 0, then AB equals 0. Our proof will have two parts. For case 1, we assume that A equals 0 and deduce the condition AB equals 0. For case 2, we assume that B equals 0 and deduce the condition AB equals 0. Assume that A equals 0. Then AB equals 0 times B by the multiplication property of equality. We shall show that 0 times B is 0. By the existence of additive identity element, 0 times B is equal to 0 plus 0 times B. Also, 0 is equal to 0 plus 0, since 0 is the additive identity element. So by the multiplication property of equality, 0 times B is equal to the product of 0 plus 0 and B. By the distributive property of multiplication over addition, 0 plus 0 times B is equal to 0 times B plus 0 times B. Hence, by the transitive property of equality applied twice, 0 times B plus 0 times B equals 0 plus 0 times B. By the cancellation law for addition, which is example 1, we get 0 times B equals 0. Since we deduced earlier that AB equals 0 times b, it follows from the transitive property of equality that AB equals 0. This completes the proof for case 1. For case 2, assume that b equals 0. By the multiplication property of equality, b times a equals 0 times a. By the commutative property of multiplication, b times a equals a times b. Hence, by the transitive property of multiplication, a times b equals 0 times a. We showed in case 1 that 0 times any number is 0, so 0 times a is 0. Therefore, by the transitive property of equality, a times b equals 0. This completes the proof for case 2 and also completes the proof of the theorem. You have come to the end of part 1 of lecture 2.1. Further examples will be given in part 2. Thank you for your attention.